yesterday. Charge, positive, neutral, negative yesterday.
Yeah.
Remember that the atomic number is the number of protons, and the number of protons is what determines each different element. You have to know all of that, including the term atomic number. Now, something that I may or may not have said yesterday, but where I'd like to start today anyway. When the baby Jesus or a pulsar / quasar makes makes atoms, and there may be other ways to make atoms, by the way, but anyway, when atoms are made, for the most part, they're pretty much going to stay that way forever. For the most part. Unless there's tremendous energy around. If we have tremendous energy, we can add or remove protons, neutrons, or electrons. It takes work to do all of those. A little bit more work for some of those pieces than others. But if we have a lot of energy, we can add protons or remove protons, add neutrons or remove neutrons, add electrons or remove electrons. So I'd like to talk about those changes. If you change the number of electrons, you're going to change the charge of the atom. If we add electrons, there's more negative on board. It's becoming negative ions. And if we remove electrons, we've left the same number of positives but gotten rid of some of the negatives. We've now created, by removing electrons, a positive ion. You should note that these changed charges are known as ions, and this affects their bonding properties. They may be more or less reactive with other atoms. Everybody clear on the ion thing? Next, if we change the number of protons, which is very difficult to do, then we are basically changing the whole element. If I've got a helium with 2 protons and I take one away, I'm left with a very heavy hydrogen. Remember that changing the number of protons, which like I said is very difficult, fundamentally changes the element. This is how you would make gold. If you wanted to be an alchemist. The one thing that we will discuss a lot in nuclear physics is changing the number of neutrons. Because their charge is neutral, it's relatively speaking easy to change the number of neutrons. It's not something you can do in the backyard. This is not for the home inventor. You're not going to build some Unabomber shed and start changing the number of neutrons. But I mean, if you've got a few $2 billion and a team of nerds and fancy engineering, you could, theoretically, change neutrons more easily than electrons and protons. Because you don't have to overcome any charge issues, any magnetism or repulsion. We say that isotopes, that's a vocab term you need to know, are versions where you vary the number of neutrons. This changes their weight, but not their charge. And thus, because it hasn't changed the charge, it doesn't change how they react with others. They would still bond or still not bond. Because we haven't changed any positives or negatives, We've just added more weight or removed some weight. Remember, different protons, different elements. Different electrons changes the charge. Those are called ions. But different neutrons are called different isotopes. A heavy isotope has extra neutrons. And a light isotope has lost neutrons. By the number of hands, I made the assumption that many of you are familiar with this information. So I've made this more of a review for kids with chemistry than a lesson for kids without. I've got a whole period to answer your questions if you have them. Or whatever, I mean, half a period? I've got half a period to answer your questions if you have them. Anyone? Bueller? Yeah.
What's the change in weight actually do?
Well, the primary difference is the attractive forces, the gravitational attractive forces within the nucleus are going to be offset. A horrible analogy that barely works is imagine a car where you've added a bunch of weight on one side or one corner of the car. Given a little bump, your suspension might bottom out and you could damage your car. If I put a huge pallet of bricks on the very end of the tailgate of my Tacoma, I can't drive at the same speed, I can't take the really big jumps. It would either destabilize or break my car. Heavy isotopes have trouble holding together. Coincidentally, the punchline to nuclear energy is if you can take one of the biggest possible elements and make it extra heavy, even heavier than it already is, it's very easy or even spontaneous for that atom to fall apart. Nuclear fission, which is the splitting of an atom, happens when a very heavy atom gets even heavier and just can't hold it together anymore, and there are too many conflicting forces, and it just splits open. And when you break a nucleus, you release energy that is immeasurable.
So when they ignite a bomb or whatever,
it's very cleanly measurable, but I need to say inconceivably hot. Yes.
Or break one of these for a power plant, are they shooting an extra neutron at? Okay.
Yep. So all nuclear energy, like what we're going to end up talking about on Monday, nuclear power is shooting neutrons at very heavy atoms, and the energy released when they break is this heat source to boil water. Yeah, we'll talk about the chain reaction. The byproduct of this is more reactions, so it's very difficult to control, but we'll get into that. Get out. Oh, are you telling me that I get to go play with my chickens now? Well, all right then. You are the first period of the day that will get 25 or so minutes to work with your groups on the solar house plan. I am willing to just plain old lecture if you guys aren't going to work. So I'm going to assume that you guys are doing solar house plan.
that was fucking bad.
You guys know how to stop this?
I think she clicks the R. She clicks the R. That's where